Hello, my name is Jillian Cukor, and I'm going to be teaching the Organic Chemistry lecture for Exam 5. So let's get started. The first topic is, what is a nucleophile? And that is the symbol that we use for nucleophile, by the way. It is the thing which replaces the group in the starting material. For example, water or iodide. Water is a weak nucleophile, and we'll get more onto that later, and iodide is a great nucleophile. Again, we'll get more into this later. Now, this is the symbol for electrophile, and an electrophile is just an electron-attracted acid. Well, that's what they are, acids, electron-attracted substrates that are positively charged. And again, there's more to be uncovered. What is a leaving group? And a leaving group is a group which departed from the starting material. And these are mostly weak bases. There will be examples where most of these are weak bases, and that's what's going to be leaving to get the product. Solvents. Well, there's two types of solvents here. There is Protic solvents, which have donatable hydrogens, for example. Basically any alcohol, and the R just means you could put anything there to which it could be an alcohol. And then we have aprotic solvents, any solvents without donatable hydrogens. So these are good examples of aprotic solvents. And again, these will be more important later on. Carbocation. Carbocation is basically which during an Sn1 mechanism, a hole is formed for the nucleophile to be with rearrangements as necessary. And there's two types of carbocation rearrangements, but basically your carbocation is this plus here, notifying that it's a hole. Basically that there's nothing there and it needs to be filled. Now, a 1,2 hydride shift is basically in which you see the hydride is flipped with the hole. And the 1,2 methyl shift is the other example, other type of carbocation rearrangement, in which instead of a hydride, it is a methyl. So the CH3, here's the hole, here's the CH3 in which it's switched with, and you can see the resulting product. Now, an alkene is basically just a hydrocarbon containing a carbon-carbon double bond. And this is a good example that is going to be most commonly used in this lecture. And this and this are basically the same thing. This is just a broken down version of that. This is going to be a useful chart for making substitutions or eliminations, which we will see in a little bit, but this is the chart that's going to be helpful when determining what's a strong nucleophile, what's a weak nucleophile, strong base, weak base, etc., etc. And I color-coded them so it will be easier for us to determine or differentiate between the 4 boxes. So let's start with strong nucleophile and strong base. An example of this would, of course, be, if I can click the pen, OH. And another example could be OCH3, or basically anything attached to an oxygen, and H2. These are good examples of a strong nucleophile and strong base. Next, strong nucleophile, weak base. Some good examples might be cyanide, azide, iodide, bromine, chloride. Another example might be NH3, or even acetate. These are examples of a strong nucleophile and weak base. Now, on to weak nucleophile, strong bases. There's not really much to this one. And for this one, I'm just going to put this. Now this has a big and bulky base, which can be used for elimination, and we will get onto that later. So I'm just going to put big and bulky. Now what can be used, since there's going to be two different types of elimination processes, we can also use tiny bases as well. Now, on to weak nucleophile, weak bases. An example of this could be, as always, water. And water will always be a good example of weak nucleophile, weak bases. Another example might be CH3 attached to OH, as well as carboxylic acids. And this is the useful chart that we will be using later on. Now keep in mind that regarding this chart, all nucleophiles are Lewis bases, meaning that they donate electrons, but a base, otherwise known as a Bronsted base, which is the base that we know, is just a name that we give when it forms a bond to a proton. Just so that you could differentiate between the nucleophile and bases in this chart, to help you better understand. Here is a chart comparing two mechanisms we're going to be looking at, Sn1 and Sn2. Now, in an Sn1 mechanism, it is a two-step mechanism where the leaving group leaves, that's what the Lg stands for. The carbocation rearranges, remember, with the hole, and the nucleophile attacks. Now there is an asterisk by two-step because the carbocation must rearrange if necessary, which adds an extra step to the Sn1 mechanism. Now in an Sn1, racemization of stereochemistry may be necessary in the product, which just basically means that you're going to have two possible products. It could be one with a hedge and a hatch. In an Sn1, you're going to have possible substrates in your product that one may be better than the other. Now in Sn1, benzylic is the best possible solution for a substrate. Then it goes allylic, which is this right here. Then tertiary, secondary, and primary. Now you should have learned about tertiary, secondary, and primaries in a previous chemistry course. But a primary substrate is to never be seen in an Sn1 because it's just simply not possible. In an SN1, any nucleophile can be used, even the weak ones, such as H2O, for example. Carbocation rearrangement is possible, as stated before during the two-step mechanism, but that doesn't mean that it's always likely. An Sn1 mechanism favors Protic solvents, my bad. And here is an example of an Sn1 mechanism. Now in this example, you can see here we have this right here, and we have the nucleophile. Now in the green, you can tell the extra step being added in the mechanism to create the product, where we have the electrons from the nucleophile going into the carbon with the hole right there, and that eventually turns into this product with the nucleophile instead of the chloride. By the way, the chloride is not attached to this right here, not attached to the molecule at all. It is actually floating in solution. When you take an extra step with the carbocation rearrangement, the leaving group is always going to be floating in solution. Now on to SN2. This is a one-step mechanism where the nucleophile attacks and the leaving group leaves all at one time. And in the product, you may see an inversion of stereochemistry. Stereochemistry is just the word for the wedge in the hatch. Wedge being this one right here, where the wedge just basically means that it's coming towards you, and the hatch means that it's going away from you. So in an inversion of chemistry where you have this at first, you're going to have this as a product. Or where you have this at first, you may have this as a product. Or if you have both, you're going to have it flipped. These are the substrates you're going to see in an SN2. Primary is better than secondary. Secondary is better than tertiary. Because tertiary will never be seen in an SN2, as for the same reason as the first one. It's never going to be seen in an SN2 because it's just simply not possible. It's not going to withstand it. There is no carbocation rearrangement just because simply it is a one-step mechanism. An SN2 mechanism favors aprotic solvents over protic solvents. And there must be strong nucleophiles only in this one. Now, if we refer back to the chart, it could be in these two boxes right here. It could be an OH, OCH3, anything attached to an oxygen, cyanide, NH3, iodide, etc. Here's an example of an SN2 where it's just a one step. You have this molecule with the nucleophile. The electrons from the nucleophile go to the carbon, and attached to the carbon is the chloride, kicks out the chloride, and you have the molecule attached to the nucleophile. And that is basically it so far. We will move on to the next portion. Now we're going to be talking about elimination mechanisms. There are two types of elimination mechanisms, E1 and E2. We're going to talk about E1 first, which is basically unimolecular, And just as a key, nucleophiles are for substitutions, which is Sn1 and Sn2. We use bases for eliminations, which are just proton acceptors. An E1 mechanism is a two-step mechanism where carbocation rearrangement may still occur via the two ways we talked about earlier, 1,2-methyl or 1,2-hydride shift. We will always get a double bond as a product in an E1, so we must know we will always make the most stable alkene. And here's an example of an E1 mechanism taking place. We have the molecule with the chloride, and here's the hole from the carbocation. And we did a carbocation rearrangement, and we use the electrons from the base to the hydrogens, and we use one of the hydrogens to take place of the carbocation to make the double bond, and there is the product. So if you want to look at it again, we have that molecule in the hole from the carbocation rearrangement, and the product. Now we're going to be talking about Zaitsev's rule, which states that the alkene that forms in an E1 is the most stable alkene in an E1. We have this as the least stable alkene, and as we talked about earlier, the alkene is this formation right here. This is least stable because it is attached to 4 hydrides, and it gets stronger with every substitution that there is with R or anything. Here's a mono-substituted alkene, di-substituted alkene, tri-substituted alkene, and the most stable is where it's completely substituted. Here is an example below where we have a molecule here. The base attacks here at this carbon, more specifically attacks to the carbocation, and then the carbon attached attacks here, which ends up with the double bond being attached right here where we said it would attack from, and the hydride. And this, therefore, is a tri-substituted alkene because you have 3 options to where it can be substituted from. Here we have an E2 mechanism, which is just bi-molecular. It is similar to an Sn2. There are 2 possible products that you could derive from an E2. Zaitsev product, which is what we've seen before, and the Hofmann product, which only uses big bases. In an E2, the base determines the product through either a normal base or a big bulky base, which we've seen from the chart earlier. In this example here, where we have a Newman projection, the green is what's closest to us and the blue is what's farthest away from us. The HB and the CL are farthest apart, and therefore these are antiperiplanar. This is the H that attacks the leaving group in the mechanism because they're so far away from each other. And here is another example, but this time with a cyclohexane, with stereochemistry, of course. The H on the wedge and the Cl on the hatch are antiperiplanar. Now this is because even though they may seem close together, they are actually farther apart than you think. Because, as I stated earlier, the wedge is facing you. The hatch is facing you and the wedge is facing away from you. So they're farther apart. And this is the H in comparison to the other H that attacks the Cl for the mechanism. And down here below, I have some examples to differentiate between E1 and E2. Now in the first example with the E1, the base attacks the carbon attached to the wedge, and the wedge attacks the Cl. Well, overall the base attacks the Cl, but little by little the Cl leaves, turns into the carbocation. There's carbocation rearrangement, and the double bond is formed where the carbocation is to become an alkene. And as you should know, they will always take the H leading to the most stable double bond. Now what does that mean? That basically means here you have one hydrogen, because this carbon is attached to two methyls already. Over here you have 3, and over here you have 3. Now which one is most stable? This hydrogen right here, if this pen works, will lead to the most stable alkene. And that's just a further description on this explanation right there. Now, for E2, now if you take a look, this base attacks the hydrogens on this molecule. The hydrogens attack the carbon, kicks out the leaving group, which is the Cl, and turns it into a double bond, and it is as simple as that. Again, base attacks the hydrogen, hydrogens attacks the carbon, leaving group leaves, double bond is formed. Now let's discuss leaving groups. A poor versus a good leaving group. In the mechanism, in either an Sn2 or an Sn1, fluoride will almost never be seen, and if it is, it won't work. That's because of its size. Now the only reason, as you can see in a periodic table, as you go down the periodic table, the size increases between these leaving groups. Fluoride is weaker than Cl. Cl is weaker than bromide. Bromide is weaker than iodide, and iodide is weaker than O2. The best possible leaving groups are these two right here, if the pen wants to work. There you go. Now these are good leaving groups, then better than these because of their large size, as seen on the periodic table. And that's how you can differentiate between poor and good leaving groups. Now let's look at protic versus aprotic solvents. As mentioned before, protic solvents are any solvent with donatable H, which, keep in mind, they favor Sn1 mechanisms, as described before. Aprotic solvents are any solvent without donatable H's, and keep in mind that they favor Sn2 mechanisms. Now the pink and blue written on the paper differentiate between the protic and aprotic solvents. The alcohols are our main focus in this lesson, and these are protic just because they have H's to donate, which are basically just acids. DMSO, DMF, HMPA are all examples of aprotic solvents because they don't have donatable H's. And keep in mind that when reading a mechanism, the NU, or the nucleophile, or the base, is on top, and the solvent, which is the protic or aprotic solvent that we're talking about now, goes below the arrow. Now, here's a little tip. Protic solvents usually slow the rate by solvating the nucleophile, and aprotic solvents increase the rate of an Sn2 by binding of carbocation and releasing the nucleophile in the mechanism. Here are some more useful tips to know for the mechanisms in organic chemistry. You might have seen these before, but here's just a recap. This arrow versus this arrow. This arrow goes both ways, meaning that it is in equilibrium to each other, or one side could be equal to the other. This arrow just basically means it goes from reaction to product. Yielding. It is yielding a product. A regular yielding arrow versus a curved arrow. Curved arrows account for reaction possibility, like we've seen before. So when we see a curved arrow, it is usually a step-by-step kind of thing. A double-headed arrow versus a single-headed arrow. Double-headed arrows usually account for 2 electrons, while single-headed arrows usually account for 1. They carry 1 electron, while the double-headed arrows carry 2. Here are some examples that we could be working on. For the first example, this is what we have, and you could pause if you'd like to practice on your own. And just so you would know, I put what type of mechanism that is. Alright, so just so you would know, it is an Sn1 because the structure is in cyclohexane. We also have the leaving group iodide. Alright, so it would be CH3CO2. So keep that. This is unchanged with the sterics. This is unchanged. And instead of iodide being there, we would actually put the CH3CO2. And because it's sterics, we're going to have 2 possible products. With racemization, all right, and that's the first one. So basically, we kick the leaving group out, and we replace it with CH3CO2 and include racemization because it includes stereochemistry. For the next one, we have this molecule with the leaving group Br. I'll give you a moment. Now notice, what leaving group is there? Fluorine, but fluorine is not a good leaving group, so therefore nothing can be done. Next one, we have this, and I'll give you all a moment. Now notice this is an Sn2, this is a benzylic, but we have 2 bromines. We are not going to use this bromine because this bromine, oh, come on, is a better leaving group because it is sp3. Now you should have learned about sp3 in previous chemistry courses. Now because it is sp3, this is a better leaving group, therefore we're not going to be using this. So, going to have benzylic, the bromine does not change, so we're going to leave that there. And instead of bromine, we are attaching that there and replacing bromine with the nucleophile. And that is the solution for that one, the product, sorry. For the next one, we have an E1, and I'll give you all a minute. All right, this should have been easy. We're going to take the double bond and that's just floating in solution. We're going to take this, put it there. Now this is a 2-step because it's an E1. We're going to have carbocation. The pen's dying, sorry. Just redrawing it. And this is what we get from the carbocation. But we can also get this product right here. Let me just draw that line. This is better than this one. This is a secondary, while this one is a tertiary. The tertiary is fastest in an E1, so we use this, and we'll bring it back up, and we will create our product. Keep the H, and we replace the hole with the Cl. And this is the product. And those are the examples.